So we've just finished talking about our methods and our decoupling mechanics right there, right? We just went through a bunch of stuff there. And now it's time to start talking about interfaces. And I think one of Go's legacies is going to be some of the stuff that I show you over the next hour or so with interfaces and composition. Now, in order to really best understand the polymorphism, there's a great quote from Tom Kurtz, who's the inventor of BASIC, and it says, polymorphism means, what he's saying here is polymorphism means that you write a certain program and it behaves differently depending upon the data it is operating on. This is a beautiful, beautiful idea for the definition of polymorphism. So you're going to continue to hear me say polymorphism means that a piece of code changes its behavior depending on the concrete data it is operating on. Everything is driven from the concrete, including all of this decoupling. And again, it's going to keep driving home the idea of data semantics, data-oriented design, everything. So I want to start out with giving you an example of polymorphism here, the idea that a piece of code changes its behavior depending on the concrete data that it is operating on. So let's take a look at that code. Now, this code is starting out on line 10 with an interface named reader, with one active behavior read. But notice something about the declaration of reader. It is a type. Type, not type struct, but type interface. Now, this always kind of freaks me out a little bit. Because it's a type, I can do the following in code. I could say var r reader. I could say let's define a variable of type reader. Now, why does this freak me out? Because interface types are not concrete types. They don't define any sort of data. They only define a method set of behavior. Think about it. An interface only defines a method set of behavior. So what that means is that interfaces are valueless. There's nothing concrete about them. Yet I can define a variable like this of named r of type reader. Yet r does not exist. So the first thing that we've got to put into our programming model is the idea that r is not real. There's nothing real about it. There's nothing concrete about it. We cannot read it. We cannot write to it. We cannot manipulate it. All right? We've got to keep this idea that interfaces are valueless. And that's going to help drive the rest of everything we're going to be talking about here through polymorphism. Remember, polymorphism means that a piece of code changes its behavior depending upon the concrete, this is not concrete, concrete data it is operating on. Now, as a side note for us to continue to talk about cost, let's go back and look at our interface declaration for a second. On line 11, I've defined a method named read that takes a slice of bytes, returns an int and or an error. Now, I could have written this method like this. And maybe the method would have been simpler for the developer to use. I could have said, well, pass me the number of bytes you want me to read, and I'll read those bytes, or at least up to those bytes. I can't guarantee I can read all of them. And then I'll return a slice back out with that data. Now, why is line 13 such a horrific API design for Go? And I want you to understand as I ask this question, API design has to be about making things easy to understand first, not simple to do. But also API design has to take into account the impact that API is going to have on the caller's program. And in order to understand the impact, you've got to understand cost, and you've got to have trade-offs here. What I'm saying to you is on line 13, the API has huge costs compared to line 11. So much so that, again, we want to make sure that we're balancing all of these things out. Now, why is this method not really a great method for Go? Well, every time line 13 gets called, there has to be an allocation that occurs on the heap. There's no way around it. And I'm going to show you why. Now you can't write methods, or you can't implement methods like this inside of a type. I'm just doing it for the visualization of it. So where are the allocations coming from? Well, the first allocation would come from the construction of the slice that you have to make, because the length is going to be set using a variable n. And I've said this a couple times already. If the compiler does not know the size of something at compile time, then that must be allocated or constructed on the heap. At this point, the compiler does not know the size of the backing array. It's based on a variable n. So boom, that allocation has to occur. Now we might say, well, I can get rid of that allocation, Bill. And what I can do is set the size myself. Boom. So I just made this API even simpler. I'm not even going to ask for a size. I'm going to try to read up to that 4,000 bytes. And if I can do it, great. And you're right, now we've gotten rid of the allocation based on the idea that the compiler doesn't know the size, because now it does. But at some point, you have to do this. At some point, you have to return that slice back up the call stack. And when you do, the pointer to the backing array now says this can't be on the frame anymore. So there's no way around the allocation with this sort of API design. And remember, this is going to be in a tight loop. So one of the things that we have to be careful about around API design is not even just our data semantics. We absolutely have to be consistent there. We also have to understand the impact that API is going to have on the user or the caller's program, and design APIs that are sympathetic with everything that we're doing, in this case sympathetic with the garbage collector. Okay, so I like this API design. I like this API design very much for our reader, and I want to continue to use it. And so remember here that reader is a type, but it's an interface type, which makes it a valueless type. And even though I can declare a variable named r of type reader, it doesn't make it concrete. From our programming model, r really does not exist. But if we switch over to line 15, what you're going to see is the definition of a concrete type. There it is. It's a struct type, not an interface, a concrete struct type. This is real. This represents real data. We can read, we can write, we can move around our program. And this type represents, in this case, a file on our file system. Now, if you look on line 20, you see a method. And that method is named read. And if we take a little bit of a closer look, you'll see that the read method matches the exact name and signature as the read method defined on line 11 inside the reader interface. And because of that, I can now say the following. The concrete type file now implements the reader interface using value semantics. Go is about convention over configuration. You have a compiler that can perform static code analysis. We don't have to configure the interface to the concrete type. There are way too many languages that would require you to do something like this. This is configuration. Hey, let's bind the reader interface to the concrete type file so we can implement these behaviors, right? All configured. This is very restricting because we're asking the developer to think about our application and our needs above their own. Doesn't work. So by the compiler being able to perform static code analysis, we can now say on line 20, because of the implementation of this read method, the concrete type file now implements the reader interface using value semantics. This is beautiful. Now, I'm going to add a second concrete type to this program. It's called pipe. Pipe represents some sort of stream, right? It could be a network, it could be streaming anything, but it's a pipe. And pipe is a concrete type. It's a piece of data that we can manipulate, read, and write, and move around our program. And pipe also implements the reader interface on line 32. Because of the read method on line 32, we can now say the concrete type pipe now implements the reader interface using value semantics. I now have two concrete data declarations, right, that implement the same behavior read defined by the reader interface. Now, how do I use all this stuff? Well, let's go and now look at our polymorphic function. So I've moved the code over here to line 50. And I want you to look at the function signature for line 50. Line 50 says that I will accept a value of type reader. Look at that right here. It says I will accept a value of type reader and return a value of type error. But this is what's interesting. I've already told you there is no such thing as a value of type reader. Values of type reader do not exist. It's an interface time. Interfaces are valueless. So if this function is not asking for a reader value, which it can't, what is it asking for? It's really saying the following. I will accept any piece of concrete data, any value or any pointer that implements this behavior, that exhibits the full method set of behavior defined by reader. This polymorphic function is creating a level of precise decoupling because it's not asking for data based on what it is. It's asking for data based on what it can do. And this is when we're kind of moving from the concrete to the decoupling world. We start asking for data not based on what it is, but based on what it does. You don't want a bill, you want a programmer. And many different people can satisfy that programming need. But if you want me, then you have to explicitly ask for me. You're no longer decoupled, right? You lose that flexibility. That's what this function is saying. It's saying give me any piece of concrete data, any value or any pointer that exhibits this behavior. And how can data exhibit behavior? Through the use of methods. So here's one case where we're going to choose a method over a function because we have a polymorphic function that's saying I don't want data based on what it is, I want data based on what it does. And now where does that polymorphism come in? Remember, polymorphism means that a piece of code changes its behavior depending upon the concrete data it is operating on. Look on line 53. On line 53, we are calling the read behavior against our valueless type. Well, if I pass a file value into this function, then we'll be implementing the file's implementation of read. If I pass a pipe value through, we'll be implementing or executing the pipe's implementation. There's our polymorphism. Line 53 changes its behavior depending upon the concrete data that we pass through this function. Now, why don't we go through and look at all the mechanics on the board to see this polymorphism in action. So on line 41, I go ahead and I construct a value of type file and a value of type pipe. So here it is. Here's the file, and here is pipe. There they are, line 41 and 42. Now on line 45, I call my polymorphic function. But I'm using the file value, and because retrieve is going to receive its own copy of the file value, what we're going to say is that value semantics are at play. I'm constantly going to be talking about what semantic is at play because it tells us the behaviors we expect to see. And value semantics are at play, which means when we cross over this program boundary, we're going to end up with a copy of F. Okay, brilliant. Now, where does our decoupling come in? Well, even though in our programming model R is valueless, and it does have a compiler implementation. Remember, this is an internal implementation that has nothing to really do with our programming model. Now, the second word of this interface value that the compiler is defining is one for storage. And remember, as soon as we have decoupling, what does that mean? It's going to mean for us that this now has to allocate. So now that's going to have to end up on the heap. That copy ends up on the heap. There's an allocation. But if we want the decoupling, then we'll take that cost. But what about the first word of this interface value R? Well, I want to show you that there's no magic. An interface value is a two-word data structure, both with pointers. And the first word points to a special table that we call the I table or interface table. Now, again, this isn't anything novel. If you've worked in an object-oriented programming language before, you'll know that those languages have something called a V table, that vector table. And it's a table that creates a mapping of function calls. And in an object-oriented programming language where inheritance is there, the V table allows a base class pointer to execute a derived object's behavior through the base class pointer. And we're kind of trying to get the same level of decoupling here. What the I table does is it lets us define the type of data that's being stored, a file value is being stored, and then it's going to give us a pointer to the implementation, okay, of read for that file. So essentially what's going to happen is this. When we call read against R on line 53, then we're going to do an I table lookup, identify that we've got a file value that is now stored in R. Once we stored this file value in R, it was no longer valueless, was it? It now represented a file value. It had concrete data inside of it. That's storage. That's the relationship between an interface and the concrete data, one of storage. Once we stored that copy in, R is no longer valueless. Now when we call read against R on line 53, we do our I table lookup. We find the actual read implementation, and we call that read implementation against our copy. Boom. Now, where does the polymorphism come in? Well, now on line 46, I'm not passing a copy of F, I'm passing a copy of P. We're still using our value semantics here. Again, that's going to be an allocation, but this is going to say pipe now, not file. And now that same call on line 53, when we call read, this time we're going to call the pipes implementation of read against our pipe data. Remember, polymorphism means that a piece of code changes its behavior, like line 53, depending upon the concrete data, file values or pipe values that you pass through. Really, really cool stuff here. Now, moving forward, I don't care about I tables. Way too technical. Doesn't make us a better Go developer. I showed you that originally because I don't want you to think there's any magic going on. So moving forward, even though we know this is a pointer, what I'm going to say is the first word is going, in this case we were using a pipe, but the first word is going to always describe to us what type of data is being stored and gives us the ability to access the concrete implementations of that data. And the second word is that pointer, which is going to give us that storage, which makes that interface value, in this case R, no longer valueless. But you have to remember, we're never passing R around the program. We're only ever passing the thing that we can pass, the concrete data that we're passing through these functions. So these are our base interface mechanics. Again, data semantics are playing a big role in our understanding of this. And we're going to be using these mechanics moving forward to understand more about decoupling in Go.